So for the final presentation of this session, I would like to introduce Professor Mizuki Tada from Nagoya University. She is a distinguished expert in catalysis chemistry and operand X-ray spectroscopy. So I will introduce short bio of Dr. Tada. Dr. Tada is a professor of Research Center for Materials Science, Department of Chemistry, Graduate School of Science, Nagoya University. She earned a PhD from the Department of Chemistry, Graduate School of Science, the University of Tokyo. Then she had appointments at the University of Tokyo Institute of Molecular Science, Nagoya University, and Riken Spring 8. She has received many awards for her excellent researches, but sorry, I cannot list them due to the time limitations. But okay, so now move on her talk. And today she will speak on light pioneering science for deep catalysis. So Professor Tada, please.
Thank you very much, Professor Harada, for his kind introduction. So I'm Mizuki Tada from Nagoya University, and it is my great pleasure to talk on our recent works on using imaging technique for the chemistry, in particular in the material science and the catalysis. So towards the realization of the carbon neutrality by 2050, a wide range of scientific and technological innovations are being actively pursued. Chemistry faces many critical challenges, including the hydrogen production or hydrogen use and the CO2 conversion and CO2 capture, and many synthesis of the materials for this kind of processes. And the catalyst, ceramics and porous materials and some materials for the electrode or fuel cell. These are typical classes of materials that play central roles in addressing these issues. And it is essential to approach the material research from multiple perspectives. The integration of the synthesis, analysis, and application of functional materials is key to deep material science now. However, as you know, the real material, which is a practical material, is not a single model, such as a single crystal, and have more complicated and heterogeneous structures. For example, so this is an example on the polymer electrolyte fuel cell, which is composed by quite many components, electrocatalyst using a metal catalyst, carbon support, and reactant product and water, electrolyte, and gas diffusion layers in simple fuel cell systems. Main catalytic reaction is molecular catalysis and conversion of hydrogen and oxygen to form the water molecule, providing electricity. And this kind of mechanism is widely investigated and well investigated in molecular scale and chemistry. On the other hand, the mesoscale reaction is black box. There are many events in a practical cell, for example, in diffusion and residence of the reactant and products, and the degradation of the catalyst and membrane. You can see the typical TM image on the platinum catalyst, which is a quite fine particle on platinum nanoparticle supported on carbon. And before the use, it was dispersed, highly dispersed in the cathode catalyst layer. And after the long time operation in a PFC, you can see the large aggregation formed in the full part of the catalyst layer after the long time operation. So the degradation occurs in the mesoscale. But this event the track of this event is quite still challenging. And device performances in the macro scale, and we need to understand the hierarchy on the structure and the reaction of the materials. And such much component and multi-phase systems represent one of the most challenging issues in the material science. And the new methodology capable of directly tackling spatial heterogeneity, temporal dynamics, and their hierarchy are required. And advances in X-ray imaging over the past decade have significantly enhanced our ability to visualize the structure of materials. However, structural information alone is insufficient to understand the chemistry involving molecular transformations. Chemical information, such as valence state, coordination structures, and chemical interaction, these are indispensable for the chemistry research. X-ray absorption fine structure is a powerful technique to provide such chemical information even for amorphous materials. So extending Zaft spectroscopy to the three-dimensional imaging requires significantly higher sensitivity than conventional structural X-ray imaging. We have pioneered a methodology that integrates three-dimensional computed tomography imaging technique with Zaft spectroscopy collaborated with Rick and Springate, and challenges the hierarchy nature of materials. So here I would like to show you the principle for Zaft CT imaging methodologies. So monochromatized X-rays were irradiated to the samples, and we are on a rotating stage. And we recorded the two-dimensional transmission image of the samples at different angles. So this is a simple CT technique, and you got the series of the 2D transition image at different angles. And then, so we scan the energies for the Zaft measurement spectroscopy. And finally, we can analyze this kind of data set, huge data set of the two-dimensional transmission images, and analyze the spectra on 2D, and we constructed these parameters. And finally, we can get a three-dimensional image of structure and the chemical state of materials, which shows us the hierarchy in the materials. And this is a non-destructive manner, and we can apply to the operand analysis using hard X-rays, and quite powerful tool for the structural chemical imaging of the characteristics and materials under the reaction conditions. So I would like to show you the scheme on the CT measurement. So we changed the X-ray energy and recorded the two-dimensional data, and changed the angle to the incident X-ray, rotating the sample, and we repeated again the measurement. So after beam time, we can draw in the sea of the imaging data. Okay, I'd like to introduce two recent examples of the application of this technique. First one is right-enabled operant Zaft CT imaging addressing fuel cell development challenges. So as you know, the fuel cell is a very clean and promising energy sources, and you can see a picture on the fuel cell vehicle by Toyota Mirai. And there are two types of the catalysts in the membrane electrode assembly of the PFC. And one is oxygen reduction at the cathode side, and the other one is hydrogen oxidation at the anode side. And the platinum is essential to promote the catalytic reaction on the cathode side. And we always use the platinum or platinum bimetric catalyst on the cathode side. So when the fuel cell vehicles such as the Toyota Mirai are seen on the road, fuel cell may appear to mature technology. However, in reality, there remains numerous serious technical challenges in this field, in particular for the use of the heavy-duty vehicles. So in Japan, many companies and universities have formed consortia through the NEDO project to address these issues. And for catalysts, key challenges including the activity enhancement, in particular in the cathode catalyst, and suppressing the degradation of the catalyst under operating conditions, and solving catalyst poisoning in real driving environment. And the membrane durability and the control of liquid water formed by the reaction under the operating conditions are also critical issues that must be addressed. And there are many challenges have been addressed by industries. Nevertheless, many issues still remain in this field. Ferrocell cell materials incorporated into a cell are composed of many different components. A large number of water are present in addition to the ferrohydrogen and oxygen and water under the working conditions. So we have developed the operand Zast CT imaging cell, and this is a type of standard cell for PFC systems, and we prepare the window for X-ray imaging. So we irradiated the hard X-ray to the sample under the working condition, and recorded the two-dimensional spectra on the catalyst layer. And after the reconstruction process, we can get a three-dimensional image in a particular area in membrane electrode assembly under the working conditions. So here I'd like to show you the example, first example, visualizing the living state of the PFC catalyst under working conditions. So we can reconstruct the morphology image and the platinum distribution and the cobalt distribution from the platinum LH and the cobalt KH Zast spectroscopy. And we can calculate the platinum oxidation state by the calculating the white line height at platinum L3H. And we can also apply an operand measurement by changing the cell voltage that shows us the redox response of platinum catalyst under the working conditions, which is strongly correlated to the reactivity of the catalyst. So this kind of three-dimensional imaging provide us structure, not only the structure, but also chemical state and reactivity parameters at each part of the membrane electrode assembly under the working conditions. And by the analysis of the Zast CT spectrum, and we achieved the visualization of catalyst degradation of platinum cobalt catalyst in the working cell. So this is an image before the ADT cross-sectional image, and after the accelerated degradation test process, this is a middle stage of ADT, and the final stage of the ADT, we can see the change in the distribution of platinum and cobalt catalyst, and also the changing in the valence state and the chemical structure of these catalysts at each stage. For example, it's a platinum, so you can see the small aggregation in the cathode catalyst layer. And on the other hand, so you can see the large decrease in the cobalt density to the accelerated degradation test on the PFC. So that they have a completely different reaction mechanism for the degradation of the alloy catalyst. And cobalt catalyst, cobalt species seriously dissolved to the depth reaction of the MEA, and the alloying of the catalyst proceeded under the working conditions. So imaging data is a huge data set. We have a 20 million data set from the one measurement. And we can obtain the many different parameters by the analysis on the combination of the imaging and the spectroscopy. So for example, in the morphology or amount of the elements and variance state or coordination structure, and we can calculate the difference of these parameters, which is related to the degradation of the catalyst. So how to understand this kind of data set by the chemistry? So collaboration with a data scientist is quite important, and we started to the clustering of these parameters obtained by the experimentally, and we analyze the unsupervised learning of the imaging big data for the degradation process on the platinum catalyst. Here, I would like to show you the one example to identify degradation-resistant regions in a practical cell. So we calculated quite many parameters, for example, in amount of the catalyst or some related to the dissolution or aggregation, and the platinum density, cobalt density, and some of the geometric parameters inside the heterogeneous structure of cathode catalyst layers. And we found that some strong correlation for some parameters, for example, in some geometric parameters in cathode catalyst layer for distance from the surface and platinum change in the platinum density. And we found that some part with a negligible dissolution under the working conditions, this yellow one. So this kind of the combination, unsupervised learning, data mining, and the imaging technique will provide some new information chemists cannot immerse in without any visualization of the materials. And we can apply to the three-dimensional visualization. Liquid water was achieved by X-ray CT technique, in addition to the visualization of the structure, morphology of each component. Under the humidified conditions, liquid water accumulated at the various locations within the membrane. By extracting the difference in X-ray absorption between the wet and the dry state, we obtained a three-dimensional image of liquid water inside the MEA. And sulfur, this is another important topic for the catalysis. Sulfur is well known as a strong catalyst poison. For fuel cell vehicles operating in air, catalyst poisoning by sulfur compounds in air contaminant is critical. When a small amount of SO2 is introduced to the cathode, the power output of the fuel cell drops immediately. Sulfur strongly absorbed on the catalyst surface, although it can be removed by applying the high potential to oxidize and wash it off. Such treatment inevitably degrades the other component. As a result, sulfur is considered one of the most serious poisoners for the catalyst. By the introduction of the SO2 and the subsequent recovery process on the catalyst, we succeeded in performing the statistical analysis of the platinum catalyst degradation in MEA. And we found that the absorption of sulfur species does not induce a significant structural change in the platinum catalyst. So the simple exposure to the sulfur compounds is not affected to the degradation. But the subsequent recovery process promoted to the aggregation of platinum, which leads to the loss of the catalytic activity. And in sulfur poisoning, understanding the nature of absorbed sulfur species is also quite important, and the complementary analysis of sulfur is highly effective. And recently, the use of phosphorus is reported for sulfur-tolerant catalyst. Nanoteras is expected to be a powerful platform for analyzing the key white elements in the catalysis. Okay, I'd like to talk on the last topic, imaging of the addressing reaction mechanism of metal organic frameworks. This year's Nobel Prize of Chemistry was awarded to 3 researchers who pioneered groundbreaking research on metal organic frameworks. Moths, which possess a large number of pores within their crystalline structures and can accommodate various gas molecules. So they are expected to find application for the gas storage and separation. For well-defined crystalline state in which gas molecules are fully incorporated, pioneering studies using X-ray diffraction have been conducted, successfully elucidating the molecular orientation of guest species inside MOF crystals. However, the absorption and desorption is dynamic processes. Until now, there have been no reports that directly visualize how gas molecules diffuse within the real materials. We focused on MOF74, in which absorption of gas molecules include changes in the coordination structures of internal metal sites, so the change in the local coordination structure of the cobalt species in MOF, and investigated to visualize how gas molecules absorption propagates within a single MOF using a dust city imaging technique. So here, I'd like to show you the example of intercrystalline adsorption and desorption for the water adsorption processes. And this is an initial state, and you can see the change in the color, which means the ratio of hydrated cobalt species. So at the beginning, all cobalt is unsaturated side without any coordination of the water molecules. And when we expose the sample to the water, so the adsorption and the diffusion proceeded inside the crystal. And we can see the change in the color when we increase the relative pressure of the guest molecules for in situ measurement. And this kind of the measurement suggests us the change in cobalt hydration in the real crystal. And we successfully prepared the isotherm for the cobalt hydration for the first time. So overall adsorption, this is a summation of the physical adsorption and chemisorption, can be measured by the conventional quantitative method by the adsorption, but we can't see any adsorption for cobalt hydration at a particular point in the crystal. So that's the CT imaging first provided us this kind of the hydration isotherm in a real single crystal. And we also found that some part with a poor adsorption behavior at the edge side of the crystal. And this trend is found for all crystals in the MOF 74. And so by the analysis of X-ray diffraction at this top side, and this shows us the poor crystallinity. And so that means some shape and crystal engineering is quite important to increase the overall performance in the adsorption in the MOF crystals. Okay, so briefly, I would like to conclude my talk. So remarkable advances in X-ray imaging have made it possible to look inside complex materials, which cannot be looked 20 years ago. We are now able to probe the internal structure and states of catalysis in materials. This is a big challenge in imaging. And such visualization have led to a deeper understanding of materials and catalysis. So now reaction under actual device operating conditions can be captured in real time, allowing us to identify where the problem of materials arise. Reaction with the materials are no longer inaccessible science now. So what is the next frontier? Is it utilizing the vast amount of information brought about the visualization, imaging, to connect it to the next innovation? I believe that the science pioneering by Wright can provide many methodologies for material synthesis and for the digital transformation of material researches. Indeed, we are already making progress based on in developing on the data-driven simulation using the imaging data and for the materials properties. And we can achieve some data-driven simulation for the practical materials to predict the function of the materials. I hope to report them in the near future. Okay, finally, I'd like to thank to my collaborators, in particular in our group in Nagoya University. This is a very strong group in the collaboration of the synthesis of the catalyst and the imaging technique. And we have, I dearly appreciate to the Riken Springett and Jasri and Tohoku University and Jais. He's a very special data scientist, and Tsukuba University and Kinki University. And I also have many collaboration with the industry. Thank you for your kind attention.